Does this creature look familiar to you? Probably, right? The Chinese spotted lanternfly, probably because they're all over all our backyards this summer. There's a bit of an infestation of these guys, and I was actually just reading an article today from the Department of Agriculture that was basically saying we should kill these things on sight because they're really bad for the environment. Apparently, they lay their eggs all over, and they don't have any natural predators because they're not indigenous to this area. They leave like a waxy sort of honeydew substance on trees that attracts all kinds of dangerous fungi and makes it hard for plants to photosynthesize. They're bad news, according to a lot of the entomologists who collect data. And I've read some studies from Penn State and also from Rutgers that talk about them. And it got me thinking that a lot of the scientists who deal with the studying and the collection of data really have to endure a lot of the statistic principles that we talk about in this chapter and in this section. So chapter 4 deals with experimental design and sampling and surveying, as you can see from the section of this, or the title of this section. So in particular, let's talk about what we're going to learn and discuss in this section. We're going to identify the population and sample, some basic vocab that you probably are already familiar with. Then we're going to talk about some vocab that we're not familiar with, identifying some different types of sampling methods and distinguishing them from one another, talking about which could potentially lead to biases and what sort of biases those are. The notion of random sampling, and then distinguishing between those two. And that's pretty much the whole section. So back to this idea of the spotted lanternfly. Let's examine a scenario here. Entomologists want to study the spread of a spotted lanternfly across Jersey, and then they break up Pennsylvania into eastern and western forests. So to document the spread, they examine trees and check them for infestations, and then document the proportions of trees in each region inhabited by these jerks. So you can imagine that we can't collect data from every single tree, obviously. So given that we can't do that, we should be asking ourselves, or the scientists at least had to ask themselves, in what way can they select a sample of trees such that this sample is indicative of the population? Which is to say, whatever proportion that I get from examining trees in my sample, I could somehow extrapolate that proportion reliably to the population as well. So if we were to sit around and actually think of this for a while, we might come up with some good ideas, and we might come up with some not good ideas. So let's throw a couple out there. We could pick a forest in the center of each section, maybe like here and here and here, and then examine all trees within a certain radius there, and then look at the proportions that are infected, and then compare them. That would be terrible. That wouldn't go too well at all, and you can imagine why, I hope. But we'll talk further later. Another thing, maybe we could break regions into counties. Pennsylvania has counties too, and then we can measure several trees at random from within each county. That might give us a basis where at least we're saying, like, all right, don't start going in the woods and counting trees. We have some kind of system by which we could block these trees up into groups and then randomly sample from those groups. Maybe that would work better. Maybe we don't look at subgroups and we just start poking on a map in random places and say, like, down here is one of my selected ones. So we get whatever scientists are in the area to pick some trees in that location, and then start examining trees in that way. That's pretty random, but also sounds maybe like a pain, maybe impractical to pull off. And there's probably some other methods too. In fact, we have a bunch of different sampling methods that we're going to talk about and perhaps look at them through the lens of this particular example. But first, let's go back to that vocab. This should be kind of familiar because I chose this as something that we talked about in the first video too, but now it's in a new context. We should be asking ourselves, what is the population in the previous example? The population being the entire set of focus for statistical study. I'm sure if you think about this, you'd be saying something related to the bugs, but actually no. What we're looking at really is all the trees, or what we want to represent rather, is all the trees in PA and New Jersey. It's more like bug infestation is the variable that was giving us the proportions. It was more or less every tree would have a yes or no in terms of infestation with the bug or not. The sample is the part of the population that I'm extracting. It's going to be the set of all selected trees. And then individuals are the objects described by the set of data. So it is each tree. Notice that an individual doesn't have to be like a person, which I'm sure we think it is what we think of when we think of an individual. And then a census is when the population equals the sample. And was this one? Of course not. We explicitly mentioned how difficult it would be to have a census. So a sampling is the next best thing, I suppose. So what we should be coming up with is that we should be trying to collect data from a representative sample of a population. And if we kind of try to lay this out like a diagram, we get this. If I can get a sample, collect data from that, then hopefully, if I did indeed collect a representative sample, I can make some inference about that and throw it back into the population. So in other words, I can get a sample proportion, maybe say that, given plus or minus a little bit due to sampling variation, that same proportion would apply to the population as well. And whatever our sampling method is, if it's going to be a good one, it has to involve an element of randomness. You know why? Usually because you can imagine again, in our example, we could probably imagine that there are some areas of Jersey that aren't as infected with bugs as other areas. And there's probably all kinds of other variables that we can't account for. So because of the diversity in our population, we usually use the randomness to take that into account, to kind of have it treated like a microcosm of the population. So randomness is one of the only ways to kind of make up for the diversity, oftentimes when that diversity is unexpected or unpredictable in the population. And the best, most random sample is called the SRS, which stands for simple random sample. Get used to hearing that. In fact, we're going to write SRS a lot in this course just because it's a lot quicker and easier and smaller. It gives us a bias-free selection of the population. There are two things that qualify a simple random sample as a simple random sample. One is seemingly pretty obvious. Each individual has an equal chance of being in the sample. So, for example, the way we were doing our sampling method a couple pages back, if we were to select some trees from our 3 regions, we'd have to make sure that every tree had an equal chance of being in the sample. It sounds very hard when we're dealing with millions of trees, doesn't it? But if I'm talking about like selecting students from Del Val, it sounds not so hard to imagine that each individual has an equal chance of being in the sample. But that's only thing number 1. Thing number 2. And pay very close attention to how these things differ, because there is a slight but significant difference. Thing number 2, every sample of size n from the population has an equal chance of selection as well. So for this one, I'm actually going to pull something up here so that we can kind of distinguish between these two things, I hope. And maybe I'll hop back and forth. One talks about every individual having an equal chance. The second one talks about every sample having an equal chance. So suppose I say I'm trying to pick 4 people from this class. Suppose this is my AP Stats class this year, and I notice that I have 4 rows of 6 people. So what if I just say I want 4 students for like something, I don't know, to go out and get me coffee. I don't know why it takes 4 students to do that, or why I'm doing it during class time. But anyway, suppose me being a terrible teacher, I say, all right, I need 4 students for this job. Fine, right column, Travis, Frank, Jeffrey, and Beth. You guys go. Suppose I even do that randomly, like I roll a die, right? A 6-sided die, and I roll a 6, and that corresponds with column 6, and these 4 have to go. Well, you can make a case that there's randomness there. Like, really, everyone in this room had a 1 in 6 chance of being selected for this endeavor, but this is still not a simple random sample, right? Again, a simple random sample's thing number 2 says that every sample of size n from the population has an equal chance of selection. So if I'm talking about samples of size 4, what is the probability that I get a sample of Iris, Effie, Matthew, and Anne? Given the method that I just used, 0. There's a 0% chance that I'll get that group because they are all in different columns. So my method, it may not matter how effective it is in terms of being a simple random sample, it's not one. So then the question would become, how could we conduct an SRS of 4 students from this classroom? What do you think? If I had to randomly select 4 students from this classroom, or if you had to rather, what would you do? How would you do it? Presumably one of the more popular answers would be to assign each student a number and then randomly generate 4 numbers within that range. So for instance, I would maybe have these guys count off 1 to 24. Then I would somehow randomly select numbers 1 to 24, and I would select 4 of them, ignoring any repeats or making sure that the process didn't have repeats in the first place. But then this might raise a new question. I could just say, why not just pick one table randomly? I kind of addressed that already. That was just more like a thinky question. It does violate rule number 2 of an SRS. Back to this now. How can one randomly select individuals from an SRS? We could assign numbers to members of the population and select. Cool, but like I was trying to get at before, like how am I going to randomly select numbers? Like what's my process for generating a random selection of numbers from 1 to 24? So one of the ways that we can do it, and one of the ways that you might be responsible for on the AP test, is to use something called a random number table. Practically speaking, we would almost never have to do this, but this is one of the only ways that the AP test can assume that you are using some notion of randomness while also checking to see that you did it correctly. Because if it was truly random, how would they know that what you got was right or wrong, right? But if they give you a random number table, then they can actually test to make sure you followed it appropriately. What it is, it's basically this thing on the bottom left, a table of randomly generated digits, or I should say pre-generated digits. One will always be given to you. Digits being 0 through 9 with repeats. So what we'd want to do if we were to use it for randomly generating a set of numbers is we would want to start at a random spot on the table, usually told to you, and then read left to right to gather our samples. A thing to note when selecting for sample, we should select the correct range and number of digits given your sample size n. So for instance, if I were to try to pick from my group of 24 students, and I started on the top left here, I said student 7, and then student 9, and then student 6, and then student 9 again, but I skip them and go to student 2. That seems fine, except for how could I even via this method possibly select students numbered 10 through 24? If I'm only selecting one digit at a time, then that becomes impossible. So I suppose one way to do it is to go 2 digits at a time, and then just ignore all the numbers that are outside of our range. So I'd ignore 79, I'd ignore 69, I'd ignore 25, 17 would be my first student, 07, aka student number 7, would be my second, and so on. You may have noticed me going from this group of 5 to the next group of 5. It's because often numbers are grouped arbitrarily to make it easier to read. There really is no reason why there's 5 here and 5 here and 5 here and so on. It's just so that if I look away in the middle of me looking at my selections, for instance, I don't get lost. Like I know where I am on the table. We should ignore everything outside of the range, like I said before. And as I also indicated, we should ignore repeats. So let's try this in a different context now. From a population of 600, I want a sample size of n equals 4. So suppose I went through the process of taking all my individuals and assigning them a number, 1 through 600, fine. And I want to grab 4 of them at random in a way that satisfies the criteria of an SRS. So suppose I make, or given a table, the table below, for example, to select 4 numbers. I should select numbers from either the range of, I've seen this before, either we start at 000 and go to 599. I'm sure computer scientists are very keen to start at 0. But we could also select numbers 1 to 600. That sounds more intuitive, but keep in mind that we're ignoring everything outside of our range. So if I go with method 1, I'm just ignoring 600 and above. But if I'm starting at 1, then I have to remember to ignore 601 to 999, but then also 000 if that shows up. Just note that both of these, depending on where we start, if we start at 0, if we start at 1, as long as we go to the appropriate value, it satisfies the criteria of being an SRS. So it doesn't particularly matter. We just need to be consistent with it. So let's actually try it in this case. Start in the block in row 2 and in column 4. So we're starting here. And select the 4 numbers. So note that we're going 3 digits at a time because we're dealing with a 3-digit population. So let's see. Looks like the first number would be 547. The next would be 721, so we ignore that. We don't reuse any of these digits, we just move along. Then 948, we ignore that too, it's outside of our range. 190 is next. 392 comes next, and then would be person, let me get there. I don't think it's going to let me. Person 70. So these would be our 4 numbers. 547, 190, 392, and then 70. Great. However, if you ever actually have to do this, and I have been in situations where I do need to randomly generate some numbers, a number table is almost never the best way to do it. Probably use your TI instead. There's technology that can simulate the notion of randomness pretty well, although it really is only simulated. And if you want to take out your calculator and follow along, you can kind of try to do this as well. Otherwise, I have an emulator that'll walk us through the process too. So if I want to, for example, in my last problem with the 24 students, if I want to randomly select them, 4 of them, let's say. Suppose I went through the process of assigning them numbers, or they called out 1 to 24 each. Suppose I started out 1 instead of 0. If I go to math and then PRB and then randint, this stands for random integer, I'm going to have to input 3 things. I want this range to go from 1, the first student, to the 24th student, and I want to select 4 students. And go. I got student 23, 22, student 4, and student 13. So there's nothing that's, I kind of just got lucky here, because there's nothing that stopped this generation process from producing a double. Like, I didn't get 22 twice, but I could have. And then the question is, what do I do then? What I could do is I could just rand int 1 to 24 1 and just keep picking a new one that's, new, actually, and isn't a repeat on the list as well. Or, fortunately, if you have a good TI, like this is an 84 silver, I guess that qualifies as good, there is an option here. Oh, I guess there's not. Shoot. I guess it's not in the silver edition. There is an option sometimes, I guess, to randomly generate integers without repeats. And that'd be the rand int no repeat button. Some of you may have that on your calculator. It'd be nice to check. So if I wanted to store this, for example, there's the STO button. This is just like, you probably won't need to do this, but this is just like a fun trick. If I want to store this in L1, it's going to just plop it there again. But if I go to stat edit, then there it is, right there in my first list, which is nice if I want to work with those numbers and do calculations, for instance. So yeah, keep that in mind. TI-84s, I guess not the silver edition, can select them without repeats, and that's rand int no rep, first lower bound, and then upper bound, interestingly. So, whoops. So I think this video is getting quite long. I'm just going to let this hang here, and I'm going to start my next video with the selection of problems. Perhaps pause it before you close this one down and think through what the answers to these might be, and then I'll start by showing those answers on the next video. So for now, thanks for watching and stay tuned for the next one.